Hello and welcome back. Thanksgiving is behind us, and so we move forward in our investigation of trigonometry. And today we're going to get our feet wet with the idea of circular motion, and we're going to build on what we learned in the previous video. Where the context is this bug on the tip of a fan traveling along a circular path. Okay, so the first question in investigation 3 asks us to, true to the theme of the course, identify some quantities here, right? So we have this, let me get my drawing tool out here. So we have this bug who is, let's see, it's difficult, 2.6 feet, 2.6 feet away from the center of this fan, on the tip of this fan blade, and we are asked to identify as many quantities as we possibly can. And again, we're going to imagine this bug traveling in this circular fashion. So I'm going to pull up this this animation that might help you identify some quantities. So why don't you start thinking about that while I toggle our animation here. All right. Fingers crossed. Good. All right. So we're going to imagine our bug at the tip of the fan blade, and let's start this animation. I'll let this run a few times to hopefully inspire you to think about the various quantities, both fixed and varying in this context. All right. So maybe we could stop there. Let's add this line. You won't even see its membership. See its measurements. Let's start the animation again. All right. So now I've added a line. I encourage you to describe what quantity. How would you describe the quantity reflected by this green line? Being extended between the bug and the fan blade. Alright, we'll stop it there. Again, all of this is just to make you, or at least help you, start thinking about the various quantities we can look at and measure. Alright, I'm sure this is probably very boring. Let me stop this now and then go back to alright. Okay, so we've done some thinking about that. Lots of different things we could look at. We want to be clear about what the quantity is, how we intend to measure it, and what, of course, its units are. So some of the things you might have come up with is, the distance in feet of the bug from the vertical or horizontal diameter. If you recall, that green line would be what? That would be our distance in feet between the horizontal diameter and the bug as it traveled along its circular path. The distance of the bug in feet from the center of the fan, is that a fixed or a varying quantity? Well, that would correspond to the radius. That's obviously a fixed quantity because it's not moving on the fan blade. The time in seconds elapsed since the fan started rotating. The bug started at 3 o'clock. So time elapsed in seconds since the fan started rotating. Some of you might have said, oh, the angular measure of the bug's rotation in radians. This is leaving something to be desired, though. It's the angular measure between the bug and what? That would be important to include. We might say the angular measure between the bug and the positive x-axis, for example, right? Since we're starting at 3 o'clock, or the bug is starting at the 3 o'clock position. We also have the distance in feet along the circular path, right? So how long is it traveling along the arc in this circular motion are some quantities hopefully we came up with. Okay, so before we move forward, I just wanted to be clear about something. So, and this is going to become, you'll see why this becomes more important later when we really get into our definition of the sine and cosine functions. But when I say here the distance in feet of the bug from the vertical or horizontal diameter. So I think it's important, for example, when we're considering distance from the horizontal, right, we would want to say, not from so much, but above the horizontal diameter, right? And again, we'll get back to this idea, but it's going to enable us to have the possibility for negative values, right? Okay, so question 2 asks us to explain how the bug's vertical distance above, that's key, above the horizontal diameter change as the bug travels from 3 o'clock in this first bullet to the 12 o'clock position. And we could go back to our animation, and I think it's intuitive enough just looking at our diagram here that its vertical distance is going to what? From 3 to 12. It is clearly going to increase. And then from the 12 to 9 position, it is going to decrease, goes down. And then it is going to, remember we're discussing above the horizontal diameter, it is going to decrease. And then again, we're going to go up from the 6 o'clock position back to the 3 o'clock position. But I guess my question for all of you is, are we saying enough? Are we being as descriptive as we possibly can in talking about these increases and decreases? All right, part B asks us to describe how the angle measure that is swept out by the fan blade change from this 3 o'clock position to the 12 o'clock position. Well, in radians, we know that there is going to be 2 pi radians in a complete revolution. So a half of a revolution would be pi radians, not 2 pi, and then a half of a half, that would be a half of pi. So we would say that theta, our angle theta, changes from 0 to a half of pi, or pi over 2 radians. Pi over 2 radians. So arguably the most, I'd say, important component of this question we need to talk about is part C, where it talks about successive equal changes of angle measure from the 3 to 12 o'clock position, and talk as I don't know what the word is, thoroughly, descriptively about what's going on with the changes, with the change in vertical distance changing, and to identify these changes on a diagram of the situation. So I want to just go ahead to D, where it asks us, and we'll come back to C, where it asks us to create a graph to illustrate how the bug's vertical distance above the horizontal diameter measured in feet co-varies with the measure of the angle theta swept out by the bug's fan blade measured in radians. So we know at 0 radians our distance from the horizontal center, if I can get this thing to work, is going to be 0. And let's talk about, since we're talking about theta changing from 0 to pi over 2 radians. Difficult to see this thing. Let's do 5. Is that 5? Hard to see. Hey, that would be our pi over 2 mark. And we know that the distance above the vertical center, the distance above the vertical or horizontal diameter, we said was going to increase, and it is going to increase from 0 to what? 0 to what? So if we need to fan animation, let's start that. And we see we're paying attention to this distance here, right? And then again, our radius is set to, I can't set it to, or maybe I could, what's our context here? 2.6. Maybe I could change that to 2.6. Let's try that. Can I bring this back? Bring this guy back. All right, now let's change this to these 2.6 feet. I might as well make this, if I can, make it 2.6 feet. Will it let me? There we go. Is 2.6 feet. All right. So let's see. All right. Okay, I'm never going to get it exactly. All right, so we're at about 2.6 feet. That's the distance of the bug to the center. That is our, that's also correspondingly the length of our radius. So if we start this and we want to sweep out this fan blade from 0 to pi over 2 radians, it's going to go very fast on me. I think that's why I elected to go with a longer radius, but right, stop. All right, so this green line segment is going to increase to 2.6, and then it's going to start to go back down. All right, go back here. So we see that the maximum distance we can achieve above the horizontal diameter is going to be there. Well, that's 2.6. 2.6. And so just really important to acknowledge is many of you probably have seen the sine graph or seen the cosine graph, and you just intuit that since our motion is smooth, we're going to have a smooth curve. But the tendency might be from some students to suggest that the graph is going to have maybe this sort of shape, right? Right, where it's not smooth. And so what I want to get at here is the understanding, the intuition behind why we have this smooth curvature here. So if you recall how we described this in Module 5, we would say that the graph is increasing, but is doing so at a decreasing rate. And I thought I'd come back to our whiteboard here, and I'm hoping the glare from the sun in this room is not disruptive enough and you can see this well enough. So if we considered equal increments of arc, that's to say equal increments in change in the angular measure, here I've tried my best to do to break up this pi over 2 radian angular change in angular measure into 1, 2, 3, 4, 5, 6 equal parts, right? And what I'm hoping to illustrate here is that, hoping you can see this well enough, is that for this first increment, our change in vertical distance is, well, I've illustrated with this blue line, right, which I've kind of brought out here so that you can see it clearly. The second increment, again, you see that, yes, the distance above the vertical center is increasing, but the corresponding change in height is smaller compared to the first increment. And then in this increment, we see it gets smaller, smaller, and smaller until we reach our maximum height, which is, of course, 2.6 feet, the radius. So, going back to part 2 of the question, we would say from the 3 o'clock to 12 o'clock position that it increased but by a smaller amount for equal increments of angular change, or equal increments in change in arc, angular change. And I encourage you to investigate, if you'd like, with the animation in your text, how we would better our answers for 12 to 9 o'clock and 9 to 6 o'clock. But that's the idea. The point I wanted to make here is that make sure we have the intuition behind from 3 o'clock to 12 o'clock. That's a pi over 2 change in theta. We're going to increase from 0 feet above the horizontal diameter to our maximum height of 2.6, and hopefully give you the intuition behind why our curve has this smoothness to it versus, say, something that looks like this or this. Okay, so true to my habits, I've already sort of answered part C for you, but it's, again, I guess worth emphasizing that for equal changes in angle measure, that the increase in vertical distance, its change decreases. That's to say, it increases, but at a decreasing rate. Again, maybe it would be useful again to just go back to our picture. We see that if we, for equal changes in angle measure, again, I've broken up this 0 to pi over 2 change in angle into 6. We see that this change in distance above the horizontal diameter, these blue lines, get progressively shorter. I've kind of tried to pull them out to the side here so you can see that, yes, with respect to the horizontal diameter, we are increasing, but doing so at incrementally smaller rate. Okay, so I just wanted to also dispel any notion that, yes, from 0 to pi over 2, we know we're increasing, and we're going to increase to our radius length of 2.6. And sometimes there might be the tendency to say, okay, well, from 12 o'clock to 9 o'clock, our distance above the horizontal diameter is going to decrease, right? And then, of course, as we travel from 9 o'clock to the 6 o'clock position, so that's from there to there, and here would be from here to here. And so, so the tendency might be to think that as we travel from 9 o'clock to the 6 o'clock position, that the distance from the horizontal diameter is going to increase, and that is true. But what we need to acknowledge is that we were careful in defining our quantity to be the distance above the horizontal diameter. So yes, the magnitude of the distance is going to increase from 0 to 2.6, but it's going to do so with respect to the horizontal diameter it's going to do so below the horizontal diameter. So we won't have something, so the tendency might be to think that we have something like this, which if I can erase with this thing, and of course I have to erase everything. I have to figure out how to use this better, right? So what we want to say is with respect to the horizontal diameter, we are going to increase to 2.6, and then we're going to decrease back to 0, and then we are going to then be below the horizontal axis. So we're going to travel in this manner to negative 2.6. Negative 2.6 is what we would call a directed distance. Since, again, we were careful when we defined our units to say distance above the horizontal diameter. And then, of course, so we're going to decrease here at a decreasing rate and then start to increase again at an increasing rate. I wanted to do, it's pi. Sorry, I wanted to do, try my best with this stylus to draw a nice curve. All right, that's negative 2.6 to 2.6, right? And of course that would be from 3 to 12, from 12 to 9, 1.5 pi. That would be from 9 to 6, and then of course from 6 back to where we started, and that would be 2 pi radians in angular change. All right, so I want to wrap this up here because this video is getting kind of long. Part E asks us if we increase the radius of the fan to 3.9 feet instead of 2.6, well then from 3 to 12 o'clock, that's a pi over 2 radian change. Of course, we're going to increase at a decreasing rate, and then we're going to reach our maximum height. Our maximum height in this case is the radius, which is 3.9 now. Horrible looking graph, but I hope you get the point. And we're going to reach our minimum point at negative 3.9. Okay, so when we come back, we'll pick it up with exercise F and work our way towards the notion of a sine curve and later a cosine curve. See you in the next video.